this example problem, it has just magically appeared at the bottom of lecture 13.2 on linearization. So, consider a vehicle suspension system that is overloaded such that its springs are exhibiting hardening behavior, such that a lumped parameter constitutive equation for the springs collectively is this nonlinear equation. So the force is related to the displacement across the spring, not linearly. This term is linear, but the other terms are the other term here is cubic, so nonlinear, with constants k and a. So you can think of a as being the sort of nonlinear part of the spring constant. So this hardening behavior is something that we'll see in springs when they go outside of their normal operating range. So usually around equilibrium or around zero displacement from unstretched spring length, the spring will be pretty linear. Actually, usually it's quite linear there, so that's good. But when you get outside of that, sometimes springs will exhibit hardening, sometimes softening. So sometimes the force will actually decrease. Well, not decrease. The force will not increase as fast as a linear spring would beyond a certain range. That's called spring softening. And it's more common, though, to see that when you stretch or compress a spring beyond its sort of nice linear operation, that it will exhibit spring hardening, where it will get stiffer as you increase. And it will not just get stiffer in a sort of new linear fashion, it'll do so in a sort of cubic way. So this is an equation for a spring that is exhibiting hardening behavior. So if you have an overloaded vehicle suspension system, it's possible that you could have spring hardening behavior that could occur because it's in operation beyond its normal displacement. So that's what this problem is about. We're going to analyze a system with that scenario. So part A is to develop a nonlinear spring mass damper linear graph model for the vehicle suspension system with input position source xs. Part B is to derive a nonlinear state space model from the linear graph using the state vector given here. Notice this is not the standard choice for a spring mass damper system. We would typically use VM and FK, but I'm choosing a different state variable for one of them. And I'll talk a little bit about why I chose that a little later on. Great. And finally, part C, we're going to use the lecture that we just did of 13.2, which is to linearize the system about an operating point. We'll say that the state variables, the operating point is that the position of the mass is 1 and the velocity of the mass is 0. And we'll also we need an operating point for our input, which we'll say is 0 in terms of our linearization operating point. So this is not an equilibrium point, but we are expecting to be operating about this point. So that's the idea. Although we prefer to linearize about an equilibrium, this is what we're going to choose as our operating point because this is the condition that we have most commonly. So this system isn't highly nonlinear, so it'll be pretty nice for most choices of parameters to linearize it if we stick around that operating point. So by computing so we're going to linearize it by computing the A, B, and E matrices of the linearized system. So the Jacobians are what we need. You might think, okay, I know the A matrix, I know the B matrix. What the hell is the E matrix? Okay, so even in linear systems, sometimes the a time derivative or time derivatives of input variables will appear in the state equations. Doesn't happen very often. We've actually ignored this fact for most of the term, but occasionally we'll have a term that'll be not just, so there'll be the A, B, A and the B matrices, but then there will also be an E matrix, which will be multiplying U dot, in this case star, but it doesn't have to be star. This doesn't happen very often, but we do occasionally see this. So something to keep in mind when you're developing your systems. If you have a time derivative of an input, it's not the end of the world. They do arise occasionally. So you just have to have an E matrix if you have a linear system. For a nonlinear system, it doesn't really matter, but when you linearize it, if you when you do the linearization, you do need to compute the E matrix as well. Great, so that's the problem we're given, and we'll go forth with part A to begin. So we need to develop a nonlinear spring mass damper linear graph model for this vehicle suspension with input position source XS. So vehicle suspension system, it's a linear mechanical system is how we're looking at it, so part A here. So let's look at a linear graph. We've got ground node. We always need a reference node in our mechanical systems, and we like to have one in all of our systems. We're going to have a position input to say like the wheel of the vehicle. So this is, we're going to treat this thing as a single spring mass damper system where the chassis of the vehicle will be modeled with some mass M, and connecting the wheel and the chassis is going to be a suspension system, which is frequently modeled, and we've modeled it before, as being a damper and a spring. In this case, it's going to be a nonlinear spring. Okay, so that's our linear graph model. And in part B, we want to derive a state space model from the linear graph model. So let's do the normal tree. Even though we're not going to use it to its full extent due to something that we'll cover in a moment, but we've got the nodes always in the normal tree, cross variable sources. The position is in a cross variable as the velocity is. So it's in a cross variable source. It's included in the normal tree, as is the A-type energy storage element, the mass, and neither of these can be included or we would have a loop, so we're done. Now, we would usually now go through and look at the different variable types, and we would select our state variables to be Fk and Vm. However, there is a sort of complication that arises in this problem. What we'll do is I will show us, as we go through, where that would occur and why I chose these different state variables. But for now, we'll just recognize that our x vector is equal to x. So the position of the mass and the velocity of the mass. Okay, position and velocity of a mass are actually two commonly chosen state variables for a mechanical system. So I did this to keep things mathematically nice, but it was also suggested by the common practice of using position and velocity of a mass for for state variables. We didn't mention an output, so we're just looking for the state vector. The input is just going to be our source, our position source. So that's pretty much that. Now we're ready to write our elemental continuity and compatibility equations. So elemental, and then we'll do continuity and compatibility. We just have three passive elements: the mass, the nonlinear spring, and the damper. So our mass elemental equation is just Vm dot equals 1 over m Fm, as always. K, unfortunately, is a nonlinear spring, or fortunately, because we get to do more interesting things now. So we typically take the constitutive equation, and to find the elemental equation, we take the time derivative of it, right? So if we took the time derivative of this, we would get Fk dot equals K and Xk dot, which is just Vk, right? The velocity across the spring. So K Vk. So far, so good. Now we've got Fk, and Vk is our secondary variable. We'll eliminate that with a compatibility equation. However, now that we have this nonlinear part, we have to take the time derivative of it, and that gives us 3a xk squared times vk, xk dot. That's just the chain rule, right? Took the derivative of the xk term, and then took the derivative of xk, gave me vk. So that is fine. Vk shows up again, but now we've got this xk term. And dealing with this xk term is challenging. I think the most promising way to deal with the xk term is to, if you wanted to do it this way, in sort of our standard formulation, where we would choose fk to be a state variable, we would want to rewrite xk as a function of fk. So xk as a function of fk. And doing that, you can do that if you solve this equation for xk in terms of fk. It's a cubic equation. There are three solutions to it. I went ahead and did this. I solved it using a couple different computer algebra systems, Mathematica and MATLAB, and they both give very complicated, it's just a complicated expression. So there are three solutions. One of them, actually only one of them is real though, so there is a single solution that we would want. However, this is just not an easy expression to deal with. So this is messy. So I almost went this way, but it's messy. So instead of going this route, I recognize that we could get nicer mathematical expressions if we instead chose to have our state variables be xm and vm. Okay? We need two state variables. It's a second order system, two independent energy storage elements. We could choose those two. There is another possibility. We could add another state variable, which is not really a good idea most of the time. Mainly, it gives the impression of being higher order, and we don't like that. So we try to keep it to a two-state variable system if we can, unless we're going to use the trick where we get rid of the input by using a the trick of taking a non-autonomous system and writing it as an autonomous system. So that's the exception. We will occasionally do that for nonlinear systems where we'll add another state variable. In this case, we can avoid it if we choose this state vector instead. So for what it's worth, I think this is a nicer way to go. So this is the direction that I am going to take us, is using this state vector. So now that we've got that out of the way, we can just write, instead of writing down the time derivative of the nonlinear spring, we're just going to write down the constitutive equation for the nonlinear spring, which is k x k plus a x k cubed. And then finally we have the damping force, which is just B V B. Okay, continuity and compatibility equations. The mass term is in the normal trait. It's a branch, so we draw this contour. We see that Fm, all the force leaving in the mass, has to equal the force going in, so Fk plus Fb. So Fm equals Fk plus Fb. And the other two are compatibility equations. They're just around this loop here. So put B in, put K in. The K1, due to the fact that we are using xk as our cross variable for this spring, we're going to write it as xk equals xs minus xm. So we'll write it as xk equals xs, the source, minus xm, which is the position of the mass. And finally, for B, we have Vb equals, we have xs, but we're talking velocity here, so it's the time derivative of xs. So Vb equals xs dot minus Vm. Okay, so we did a compatibility equation in position, and we did one in velocity. Okay, and we chose position because this variable here, this secondary variable, if you will, needs to be eliminated, and it's a position. So we wrote it in terms of position. For velocity, this one needed to be in velocity, so we wrote it in velocity. Okay. So now we'll do our usual thing where we substitute in these continuity and compatibility equations into the elemental equations, and we get Vm dot equals 1 over m Fm. Oh, sorry, not Fm, of course, that's what we're doing in this step. Fk plus Fb. And then Fk is equal to k, instead of being xk, we're going to put in xs minus xm. Plus a xs minus xm cubed. Finally, Fb equals b Vb. So instead of Vb, it's going to be xs dot minus Vm. And what we've got here are 3 equations. Vm dot is the time derivative of one of our state variables, the second state variable, Vm. However, we don't have an equation that shows up here for xm dot, right? That's our other state variable. Our x1, our first state variable, is the position of the mass, xm. So we don't see xm dot showing up. And it turns out that our choice here is a pretty common choice, in part because it gives us a state equation very, very easily, which is to say, if you took the time derivative of xm, it is by definition just the velocity of the mass, which is the other state variable. Okay? State variable. So this is a state equation. So we already have one, and we actually have had one since we wrote this as our state vector. This one is sort of comes for free. So really all we're looking for in the rest of the analysis is the state variable, or is the state equation for Vm. So we're looking for an equation in Vm dot. And we can actually do that here by substituting these 2 lower equations into the first equation. So that'll eliminate everything except xm, vm, and xs, and then there's a time derivative of our input this time, xs dot. So rewriting this, we'll call this the other state equation. Then is, we have Vm dot equals 1 over m times fk, which is the second equation, so k x s minus x m plus a x s minus x m cubed plus b x s dot minus v m. Okay, so that's one of our state equations. The other one, the free one, is that xm dot equals vm. So now we have both of our state equations, and essentially these two together are our state space model. We could write it like this. We could say our x vector dot, which of course is equal to xm dot vm dot equals, and the right hand side of each of these equations we'll just shorthand as f1 and f2. Okay, so this one will be f1 because xm is the first of our state variables, and this one will be f2. Okay, so the right hand side here of each are f1 and f2. Okay, so we don't need to rewrite. I could rewrite them here in a big vector, but there's no need to do that. So I'll put this as our answer to part B. So this is our nonlinear state equation. And now we're going to linearize the system about this operating point. We need to compute the A, B, and E matrices. So I already described what the E matrices are for you. So the E matrix is. So we'll just go forth and compute these then. So compute A, B, and E. So let's compute. So for part C, computing the Jacobians. So we know that Aij is equal to, so the ij component of the A matrix is equal to the derivative of fi with respect to xj evaluated at the operating point, which I'll just write as OP because I don't have to rewrite that a lot. So this, I guess I'll put arrows here. So this gives us A11, which is equal to, so it's df1 dx1. So df1 d, so what is our x1? It's xm, right? The first state variable xm. So f1 is this. Our first state variable is xm, and it doesn't appear explicitly here, and so that derivative, well, evaluated at the operating point, of course, that derivative is equal to 0. Okay. We also know that A12, which is, of course, df1 d, and now dx2, but x2 in this case, the second state variable is vm. Okay, so that's equal to dvm dvm, which is just 1. Okay, so 0 and 1 are the first two components. The next one, A21, is equal to the derivative of f2 with respect to xm evaluated at the operating point, which is equal to, if we look at f2, which is this long right-hand side of this equation, we need to look for the terms that have xm. So I see an xm here, and I see an xm there, and there's no xm in that term. So these two terms are going to be non-zero. And this first one, if you actually expand it a little bit, we see it's just negative k over m. So you have a negative k over m. And the other term here is going to be 3a xs minus xm squared, so plus 3a, there's going to be an over m here too, right? xs minus xm squared times the time derivative of this expression, the inside the cube, with respect to xm, which is just negative 1, right? So times negative 1. So this simplifies to, we got to evaluate this at the operating point, right? Now the operating point says that xm is 1, so if we go back up here, it says that xm, our first state variable, is 1 VM, our second state variable, is 0, and the input, which is XS, is 0 at our operating point. So we can plug in 0 for XS and 1 for XM. So this is going to be 0. This will be 1. And that gives us, this negative sign comes out. We have negative K plus 3A. So negative 1 squared is just 1, doesn't do anything, divided by M. So that's A21. And finally, our A22 is dF2 dVm, evaluated at the operating point, which is, if we go up to F2, respect to X2, which is Vm, this is the only term that has Vm in it, right? Right here. So we get negative B over M as our coefficient of that, which is also the derivative. So negative B over M. We don't have to evaluate this at the operating point because none of the state variables show up or inputs. That's because this term was already linear. Okay, so here's our A matrix. If we put them all together, then the A matrix is the 1, 1 term was 0, the 1, 2 term is 1, the 2, 1 term is negative K plus 3A over M, and the 2, 2 term is negative B over M. So this is our new A matrix. That's part of our answer. Now we can do the B matrix, which from the equation given in the lecture is just the derivative of Fi with respect to Uj. In this case, we only have one input, so it's the derivative of F1 with respect to our one input, XS, and then the derivative of F2 with respect to XS. So this tells us that B11 is simply dF1, so F1 is the simple one, remember. Time derivative of that, or sorry, not the time derivative, the derivative of this with respect to XS is 0. We have no XS dependence on the right hand side, so that's 0. I could have written it out here, so dF1 du, or dXS equals 0. And B21 equals, we have dF2 dXS, the input variable evaluated at the operating point, equals, so if I go back up to our F2, the long expression here, I find our XS terms, which are here, and the time derivative shows up here, but we're going to deal with that with the E matrix, remember. So we're going to ignore this XS dot for now. XS, XS, so these two terms are going to have non-zero derivatives. So we'll have K over M for the first one. So K over M plus the other term is going to be 3a xs minus xm squared times 1, right? The derivative of xs with respect to xs is just 1. So 3a xs minus xm squared. 3a, and there's going to be an over m here too. Xs minus xm squared evaluated at the operating point. The operating point is, again, just 0 for the input, 1 for the state variable 1, the first state variable, which is xm. And so this is just equal to k plus 3a over m, because negative 1 squared is just 1, so that's our B21, and therefore, so now that we've got both of those terms, we can write our B matrix explicitly. It's a 2x1 matrix, 2 state variables, 1 input. And we've got 0 and k plus 3a over m. And that's another one of our answers. Finally, we have the E matrix, Eij equals d fi d, and it's going to be u dot j. So we have only a single input, so we're only going to have a single time derivative of our input. So we've got E 1 is the derivative of f1 with respect to xs dot, and that is, if we look at f1 again, f1 is just vm, so there's no xs dot term in it, therefore this is 0. And of course this is evaluated at the operating point. It's hard to remember to write that over and over again. And then E21 is going to be equal to df2 dxs dot, which is equal to, if we look at f2, here we have xs dot showing up precisely once, and it has a coefficient b over m. If you take the derivative with respect to xs dot, you're left with just the b over m. And therefore, we have our E matrix. E equals 0 b over m. And that is our third part of our answer. So the 3 Jacobian matrices were all that were needed. So just to sort of round it out, we can recall that our new state vector is, the starred version, is going to be the original state vector minus the operating point. That's what we said in the lecture. So in this case, it's going to be xm and vm minus 1, 0, which is just equal to xm minus 1, vm minus 0. Okay, our u star is, according to the lecture, u minus the operating point. Oh, I didn't usually put p, I just put o for operating point in the lecture. So that's just going to be 0. So xs minus 0, which is just actually just equal to our xs. Okay, and our u star dot, we could just take the time derivative of this, directly. We could do this whole subtraction thing, yada yada, but essentially we could just take the time derivative of x of u star, which would give us xs dot. Okay, so in these new state and input variables, which the only one that changed really is the first state variable xm, then we have a state space model, which is x star dot equals a x star plus b u star plus c, or not c, e u star dot, which of course we chose E, if you're wondering why E, because we have A, B, and then we chose C, D to be our output matrices, so now we're left with E and F. And if a time derivative of an input appears in the output equation, we use the F matrix to capture that. So, yeah. That's our whole model kind of all together. I really only asked for A, B, and E, so did a little extra there. And now I just wanted to conclude this example with a comment, which is that there is a way to get the linearized model to this much quicker, and we'll get the same result in the end. And that method is to simply linearize the single nonlinear equation here. So if you linearize this equation by doing a Taylor series expansion about the operating point, then the rest of your analysis is just standard linear analysis, okay? And we get the same A, B, E matrices at the end. Now, I chose to have us find the nonlinear model for a couple of reasons. One, I wanted us to apply the technique that we learned about linearization in this lecture. But the second reason is that if you linearize the constitutive or elemental equation for your nonlinear component, and then you do the analysis, you never do get the nonlinear state space model. And if you're going to try to do some sort of nonlinear analysis with it and not just linearize, you're going to need that nonlinear state space model. So I want us to know how to find those nonlinear state space models and then linearize from there if we want to. But I also want us to realize that we have some techniques. So we're going to learn some phase space analysis techniques, and then we're also going to learn how to use some numerical solution techniques to learn a lot about a nonlinear system from its state space model. So I don't necessarily discourage you from linearizing the individual components and going from there. That's actually a much easier way to go if all you're looking for is the linearized model. But I want to also highlight the fact that if you do that, then you won't get the nonlinear state space model, which is actually pretty valuable. So that was kind of all I had for this.